I guess some of the intuition of the proof of this this sort of automated inequality prover. But I guess, yeah, so I should say by, sorry, can I write on this or no? No. Okay. Okay. Sorry, and I have 20 minutes roughly? Okay. Okay, yeah, sorry. I should have said this yesterday, but so yesterday I was talking about kind of this idea of trying to get sort of instance optimal algorithms. So this is like not a new thing. So in kind of the CS theory, game theory, there's been a long line of work trying to do this. Some really nice work on so geometric algorithms trying to get sort of instance optimal in terms of runtime. A lot of game theory work on instance optimal in terms of, you know, revenue maximization. And then related to this distributional stuff, there's a lot of work, a lot of it actually from Alon Orlitsky and his group and his students and on. So yeah, so this isn't a new idea, but I'm trying to push people to think about this. These problems really in terms of how do you get sort of provable guarantees and algorithms that really work nicely in practice. Okay, anyway, so today I was going to try to give some high-level intuition of this characterization of inequalities. So I guess the theorem is the following. So given some sequences, AI, BI, and CI, and say each of these has R terms. So the theorem is it holds that for all positive sequences, xj and yj, the following is true. Product over I, the sum over j of xj to the ai, yj to the bi, to ci. This is always greater than 1. If and only if this can be expressed as a finite product of holder type inequalities and LP monotonicity inequalities, which I'll say in a sec. So by finite, I mean polynomial in R. I guess it'll probably be something like R cubed. In practice, R is usually like, at worst, 5 or 6, but so finite. Okay, so this is kind of the first claim, and the second claim is that in some sense this characterization is algorithmic. So there exists an efficient algorithm, polynomial in the representation lengths of A, B, and C, that will tell you, is this always true? If it is, it'll tell you how to prove it. It'll tell you this decomposition. If it's not true, it'll give you some witness. Algorithmic / constructive. Okay, so just I guess I'll write it here. So, okay, so so what's Holder's inequality? What are these LP monotonicity inequalities? So I'm just going to write them here because we're going to refer to them. So, okay, so the usual Holder inequality says if you have some lambda in 0, 1, then sum over aj lambda, sum over bj to the 1 minus lambda. This is greater than or equal to the sum of Aj lambda Bj to 1. Okay. So these A's and B's are positive. Okay, and of course we can put any combination of powers of x and y in for the A's and B's. Okay, so what does this mean? This just means that for any say A1, A2, B1, B2, just plugging in xj to the A1 times yj to the B1 in here, and the corresponding thing here with the 2's, we just get equal to the corresponding thing. Okay. Yes. Okay. So this is our Holder inequality, and the analogous sort of LP monotonicity inequality. So this is just the fact that the LP norm of something is monotonically decreasing, I guess, as a function of p. So this is just the sum of Aj lambda less than or equal to sum of Aj to lambda, I guess for any lambda in 0, 1. And again, we can plug in any kind of xj, yj thing in for the A's here. We'll do it. Okay. So how would we try to go about proving this? So I just wanted to give one example which gives some intuition that we probably shouldn't. You could try to express some program that says find me sequences that invalidate this. Okay? And I just want to give one example that illustrates that this is actually not a good way of going about this. Okay? So one example. So for some epsilon that's greater than or equal to 0, consider the following thing. So sum of x minus 2 minus 1, sum of x minus 1, the 2 minus, so minus 2 minus epsilon. Okay, so this corresponds to this thing where all the y's, the coefficients of y are all 0. And it's not too hard to convince yourself. So this holds true if epsilon equals 0. And it's false for every positive epsilon. So in other words, there exists a sequence x that falsifies it. For any epsilon greater than 0, there exists a sequence of x's that falsify this. But the shortest counterexample, the shortest falsifying sequence is a sequence of length exponential in, I guess, order 1 over epsilon. Okay? So in other words, if you want to try to, what's the moral of this example? The moral is, if you want to try to prove this, you shouldn't be trying to construct something that will actually populate these sets, x's and y's. Okay. Because there might be extremely long sequences. Okay, so how should one think about this? So I'm going to give a nice geometric interpretation of how to think about this, and the proof will more or less fall out via some LP programming. Are people okay with this? I don't really want to give the intuition for what's going on, but...
But is it supposed to be easy to see that for all epsilon positive, you can find a sequence that will violate it? If not, that's fine, but...
No, okay, it shouldn't be easy to see, but this x to so this is just the number of elements of the sequence, and basically you're kind of going to play off this epsilon with, it shouldn't be obvious. Yeah, I just wanted to kind of give you the flavor of what these sequences look like. So in particular, we don't even have two different, there's no y, it's just one thing. And even just for these, we have a term that's basically the number of terms. There's some epsilon there, and that's kind of, just notice kind of the flavor of this. It's something very reasonable, but one of the exponents is just shy of what you want it to be.
So Greg, I'm understanding, on the left, there's sort of a finite number of AIs that you're given.
Yes.
And on the right, we're allowed to take sequences of arbitrary length.
Yes. So I give you Holder's inequality corresponds to, right? There are three terms: this term, this term, and this term. So these A's, B's, and C's are sequences of length 3.
Oh no, I'm sorry. Okay.
And we want to know. You give me this. Do you want to know? Is it true that for all positive x's and y's?
All positive sequences of x's and
yes.
y's. Okay.
Yes.
Sorry. No, I was just confused.
Yeah. So this is, proving inequalities like this, I don't know, it comes up more than I would wish in my life, and yeah. Okay. Okay, so to try to get some geometry out of this, think of the following. So, okay, so I claim that any positive sequences x, j, y, j, they define a function. They define some function L, which maps the plane to the real numbers, where L of a comma b is equal to the logarithm of the sum over j of xj to the a, yj to the b. Okay. I'm defining this function L. What properties does L satisfy? Well, what is this? Well, this is like the logarithm of one of our terms. So if we had taken the log, what does Holder's inequality say about L? Any guesses? So if we take the log of Holder's inequality, what do we get? We get that lambda times L of a1, b1 plus, the logarithm of this term plus 1 minus lambda L of a2, b2 is greater than or equal to L of, this thing, the convex combination of a1 and a2. So lambda a1 plus 1 minus lambda a2, comma, the thing with the b's. What is this? It says that L is convex, right? Okay, good. So what do we know? So L is convex. What does this LP monotonicity tell us about this function? Well, again, just taking the logs, it says that lambda times L of a comma b is less than or equal to L of lambda a comma lambda b. So this is from Holder. And so we also know that lambda of L of a comma b is less than or equal to L of lambda a lambda b. So what does this mean? So this is a function from the plane to R, some surface. Holder's inequality tells us it must be convex. This says if you take any point on this surface and draw a line towards the origin, if you draw the secant line from the surface towards the origin in the xy plane, in the AB plane, it tells you it must pass it must pass through or above the origin in the y direction. So we have this convex surface. Any secant that goes towards the origin, it must pass through the origin or above the origin. Right? That's what this tells you. As you go towards the origin, the actual value of L is greater than what happens if you just interpolate this point towards the origin. Okay, so these are two things we know about L.
Is there some condition under which the second could follow from convexity?
Say this once more.
See, the second inequality, it doesn't follow from convexity under some other...
Awesome question. So the question is basically, are these two really different inequalities or not? And I think they are. I mean, if you look at the case where Holder's is tight is different when this is tight. The case where this is tight is just where it's a single element. The case where Holder's inequality is tight, or where these two things have the or have the same proportion. Right? Great question. So initially we didn't know about this, and we just thought maybe Holder's was all there is. The proof almost goes through, but then basically you're trying to say something about this convex thing, but there's nothing keeping it up from below. Like there's none of this weird secant property going through the origin, blah, blah, blah. And somehow the proof falls out from beneath you in a very literal sense. So I think this is actually, it is different. Okay, so armed with this geometry, the proof is basically going to say, you give me any function L that satisfies these two properties, and I will be able to populate it. I will be able to find sequences x and y that realize your function L very closely at whatever finite set of points you wish. Okay, so I'll just write what I actually mean by that. Okay, so the proof of the theorem is basically the following. We're going to construct a linear program. That has R variables. The variables, I'll say Li, and you should think of Li as being a proxy for Li should be roughly L of AI comma Bi, which is going to be roughly the log of, think of it as the log of the sum of x to the AI, y to the Bi. Okay, and the linear program is basically going to say, can we find some function L satisfying these properties that violates this? So namely, it's going to say minimize the sum of Ci times Li. Ci times Li is literally the logarithm of this expression. When you interpret Li as this form, minimize this such that, what are the constraints going to say? Well, the constraints are going to say, look, Li should actually be sort of consistent with something like this, such that, let's say the convex or the lower convex hull, the lower hull of the set of points AI, Bi, Li is convex. And then our second constraint, namely, any secant to this lower hull that goes towards the origin must pass through or above the origin. Okay, so what's going on? So the first claim is, I claim that these constraints, I mean, you can write these as some as some finite set of holder type inequalities and LP monotonicity inequalities. So I claim that you can actually write the constraints of the linear program as holder and LP type monotonicity, and LP monotonicity inequalities. Given that, this ends up being a homogeneous linear program. The right side of all the constraints are 0. Okay? So if the minimum of this is 0, this means that by LP duality, there's a finite positive combination of the constraints which verify, which end up implying that this is like greater than or equal to 0. Okay? So if the minimum is 0, then linear programming duality gives you a proof of this via combinations of these constraints, which is exactly our algorithmic characterization. Okay. If this is less than 0, if the optimum is less than 0, then we basically need to show that these constraints on Li are sufficient in order to construct these sequences x and y, which isn't so hard. Okay? So this is basically saying you're telling me what you want the log of this sum to be at a bunch of points, and I just need to find x's and y's that are very close at these points. Anyway, so I thought, is this okay? Some people look happy, some people don't look happy.
We can ask questions while the next speaker
So this holding or not seems super fragile to the AI's BICIs, right? As you showed in your counter example, if you shift 1 by epsilon, then it does not get satisfied. So I was curious to know that in the software that you mentioned yesterday, how do you take care of these numerical precision issues?
Okay. So because we're dealing with the L's, not with the sequences x and y, it actually ends up being extremely numerically precise. So like we have this MATLAB code, it'll literally write out in English, your thing equals the product of these holder inequalities and these LP monotonicity inequalities. So it's because we're working with these L's, we're sort of allowed to scale things. So basically, I mean, yeah, if you can falsify this, you can falsify it by as much as you want. Okay? And because of that, you sort of things end up being robust in this view. And I guess, yeah, just one last comment was the geometric game I showed in yesterday's talk where you're sliding points around. This is literally playing with the dual constraints, trying to prove your thing and trying to prove the dual. So that game is literally like, what can you do with the dual of this linear?